Hi, Assalamualaikum. We are from Group 1. We are going to present the latest technology of train. So, here we go. Introduction of trains. Trains might not get the same attention as planes, rockets, and automobiles when it comes to innovative form of travel. But don't think for a moment that big steps aren't being taken to drive the future of rail travel. Trains are one of the most eco-friendly forms of transportation, and depending on the destination, they can get passengers from one city center to another in an incredibly fast time. The technology are used superfast maglev train. Maglev trains are currently the fastest form of rail travel in existence. The 90-mile journey takes approximately 7 minutes to complete at speed of 268 miles per hour. Incredibly efficient autonomous train. The systems are constantly improving and can be used on increasingly longer trips worldwide. This automation has a great potential for optimizing the efficiency of public transport systems, such as underground rail by accounting for peak time and preventing small delays. Smart sensor for automated track and train inspection. The electromagnetic technique was one of the primary tools for inspecting rail internet defects in high-speed networks until 1953, when ultrasonic transducers were introduced to railway inspection. Since then, various inspection methods have been used for monitoring the health of railway infrastructure or as a preventive measure against rail failures. The system is so accurate that it can identify any break in a rail track using GPS positioning that locates a break edge within 100 mm. Aerodynamic and efficiency. Aerodynamic must also make the train stable because as speed increases, crosswind stability decreases. To ensure the passenger safety, specifically for trains moving at more than 120 km per hour. How it makes superfast maglev train. In maglev, superconducting magnets suspend a train car above a U-shaped concrete guideway. Like ordinary magnets, these magnets repel one another when matching poles face each other. This floating magnet design creates a smooth trip, even though less train can travel up to 375 miles per hour. A rider experiences less turbulence than on traditional steel wheel trains because the only source of friction is air. Incredibly efficient autonomous rail, the train is driven without any existent system. The driver drives the train based on sight, while stationary light signals control railway operation. The automatic driving system has complete control of the departure movement between stations, automatic and precision stopping of the train, and the opening and closing of the door. If necessary, the doors can be automatically opened again, according to the system's analysis of the situation. In the case of high passenger volume, additional trains are automatically sent into operation at the touch of a button. However, an attendant is still present on board to intervene in emergency or unusual situations such as a system failure. Smart sense Smart sensor for automated train and train inspection. If there is a break or chafing in the trail, the amplitude of the wave received by receiver will be reduced and an alarm signal will be sounded. Wayside detector sensors are attached to the track or positioned at a certain distance from the track. Movable detector can inspect and monitor rail and track condition while train is moving. Aerodynamic and efficiency. Trains operate near the ground have much greater length to diameter ratio, pass close to adjacent structure and each other, are more subject to crosswind, and travel at lower speed. Trains on some routes operate in numerous tunnels, with consequent tunnel entry and exit events. Technological scheme of train aerodynamic involve the optimization design of the streamlined head and the smooth design of the body surface. Optimization design of the streamlined head includes conception design, project design, numerical simulation, and a reduced scale test. Smooth design of the body surface is mainly used for the key parts such as electric current collecting system, wheel trucks compartment, and windshield.
Next, how to apply this technology for superfast magnetic train. There are two types of maglev are in service, which is electromagnetic suspension (EMS) and electrodynamic suspension (EDS). Electromagnetic suspension uses the attractive force between magnets present on the train sides and underside and on the gateway to levitate the train. Operation on EMS, called thrust rapid, employs an electromagnet to lift the train off the gateway. The attraction from magnets present on the underside of the vehicle that wrap around the iron rails of the gateway keep the train about 1.3 cm above the gateway. Electrodynamic suspension is used to repel the train from the gateway rather than attract them. These magnets are supercool and superconducting and also have the ability to conduct electricity for a short time after power is cut. Next, for smart sensor for automated track and train inspection. The important factor in automating railway is the sensing and utilization of large amounts of data that comes from the railways, trains, and passengers. For example, is broken rail detection, or called BRD. BRD is designed for easy installation and operation on various rail-based vehicles. The sensor identifies breaks before a conventional track circuit could detect an electrical disconnect in the rail. Any break in the rail can be identified with a very accurate GPS position within 100 mm for ease of identification and repair. On board, BRD reports to the back office system to verify any detection. Then messages are passed to the signaling system or train control to take immediate action on the next trains passing the located breaks. This system closely monitors the rail network during operation. Every train is equipped with a pair of a sensor while the train is moving. These sensors scan the track. An on-board unit sends the collected data to the control center. Within seconds of a broken rail being detected, an alert is sent to following trains, or the interlock gets the information to block the respective line, or data is transmitted via a secure VPN connection. Next, for aerodynamics and efficiency. A new aerodynamic technology aimed at reducing fuel and locomotive emissions from double-stack intermodal freight trains while at the same time optimizing operational efficiency and safety. A double-stack intermodal train accommodates freight containers placed two high, one on top of the other for improved freight quality and rail car utilization. Positioned on top of the first freight container, the 48-feet rowage vehicle's innovative taper body reduces aerodynamic drag by allowing air to flow more easily around the train. For example, unveiled in 2010, the company's Zephyro VHS train set a new benchmark in terms of low aerodynamic drag and high stability under crosswind conditions. Designed using bionics, the application of biological methods in nature to the study of engineering systems and sophisticated computer modeling techniques. The Bombardier Zephyro achieved an aerodynamic drag reduction of 25% up to 50% less traction energy usage and a decrease of the wind force on the lead car equivalent 5 to 7 tons of additional ballast. Next, for incredibly efficient autonomous rail, there are many grades of train automation. First, driver control mode. The train is driven without any assistance systems. The driver drives the train based on sight, while stationary light signals control railway operations. This is the prevailing system in train commuting in major cities all over the world. Second, partly automated mode. The driver still has control over driving and braking the train manually. However, a train protection system continuously monitors its speed. Additionally, statistical information on current movement order of other trains in the network is continually displayed in the driver's cabin for assistance. Third, semi-automated mode. The sole job of the driver is to start the engines. The automatic driving system takes over after that. It has full control over the movement of the train between two stations, including the precise stopping of the train at the platform and the opening and closing of doors. 5.
Now, I will share with you guys how this technology can relate to physics theory. First, superfast maglev train technology. In the 21st century, there are a few countries using powerful electromagnets to develop high-speed trains called maglev trains. These trains float over guideways using the basic principles of magnet to replace the old steel wheel and track trains. There is no real friction to speak of, meaning these trains can hit speeds of hundreds of miles per hour. Yet high speed is just one major benefit of maglev trains because the trains rarely, if ever, touch the track. There is far less noise and vibration than typical earth-shaking trains. Less vibration and friction results in fewer mechanical breakdowns, meaning that maglev trains are less likely to encounter weather-related delays. Next, smart sensor for automated track and train inspection. Siemens broken rail detection. BRD closely monitors your rail network during operation. Every train is equipped with a pair of sensors on one of the bogies. While the train is moving, the sensors scan the tracks. An on-board unit sends the collected data to the control center. Within seconds of a broken rail being detected, an alert is sent to following trains, or the interlock gets the information to block the respective line. All data is transmitted via a secure VPN connection. The output can be integrated into existing signaling and maintenance solutions. A technique is presented to identify broken rail. The technique is based on elastic guide wave propagation through the rail. Broken rail detection is possible by either utilizing an impact device or energy propagating from the train wheel in contact with the rail. In principle, elastic guided wave energy propagates along the track, a natural waveguide, until a broken rail is encountered. Pulse echo reflection is then used to identify broken rail. Next, aerodynamics and efficiency. With the increase of running speed of high-speed train, when the train travels in the embankment air barrier, aerodynamic acting force, drag force, lift force, and side force. and aerodynamic moments, overturning moment, shaking moment, and nod moment, formed by each train body increased sharply. In subsequent researches, dynamic computation of the high-speed trains can be taken into account for further assessment of safety and comfort during a high-speed train passing at the embankment air barrier. Last, incredibly efficient and autonomous rail. Driverless trains are energy efficient and economical due to optimized acceleration, traction smooth, braking and control power intake. Based on line data generated by the control centers, the automated system calculates precisely where and how the train should be accelerated or braked in order to time the arrival and departures with maximum accuracy. The technology employed in driverless trains is called communication-based train control. This technology involves communication between the train and equipment on the track for the management of all rail traffic. Thank you. That's all from us.